In the previous episode, we created a custom layer in the Yocto project. We're going to use that custom layer to create a patch for the device tree so that we can enable one of the I2C ports on the board. To start, I recommend looking at the datasheet for your particular board. In this case, ST has it for the MP157 development boards, the DK1 and the DK2, which are a little different, but I'm using the DK1. These boards, or actually the chip, the MP1 chip, has 6 different I2C buses, and we need to look at this datasheet to figure out if and where those buses are routed in order to attach a sensor to one of the I2C ports. So if I scroll down here to page 8, you will see that a couple of the I2C ports are already assigned or already being used for a number of peripherals attached to the chip on the board. Now, because things are addressed on I2C, you could potentially use I2C1, but just know that it's already been configured to work with the LCD touchscreen or the power management chip, and I2C4 goes to the USB Type-C connector. They're being used. We don't want to change their configuration because that might affect how they're working with these various peripherals. So if you know that your part, in this case a TMP102 sensor that we're going to be adding, isn't going to conflict, whether it has the same address or it needs a different clock rate, then you should be able to add it to one of these ports. However, what I want to show you is how to enable a different port so that you don't have to worry about these conflicts. Because if we scroll down here to page 31, you can see that I2C port 5 is available on this Raspberry Pi style header, specifically on pins 3 and 5, which should be here and here, these 2 pins. You'll note that in Core Image Minimal, or rather our custom image that we've been using, it does not enable this port by default, which means we have to enable it by going through and patching the device tree. And the device tree is just something Linux uses in order to figure out what drivers to use when it's bringing up the board so that the kernel can talk to various peripherals using any number of ports, whether they are sensors, USB ports, HDMI, and the like. Device tree files or sources look like C-style coding that are kind of like configuration files. And in the process of that, we're also going to be adding something to /dev so that we have user space access of this port so that we can use it. I will probably say it again later, but I'm going to make a note here now that I2C does not play very well in Linux. If you're trying to write an application for something with I2C, you're generally better off writing an actual device driver that gets loaded into the kernel and talks to your device. We're not going to cover driver writing in this series. That's something for a later time or something else. I'm just going to show you how to enable this port so you can use it in user space if you want to create your own application, which we're going to look at in the next episode. There's some reasons I2C does not work well on Linux, and it has to do with how some of the communication systems work, where you hold one of the lines high after, say, a write, waiting for a read, and because we're going to use a file I/O control to do that, you may not be able to do some of the tricks that I2C devices require. But the TMP102 works just fine because it's dead simple. And we're going to attach it to these pins, specifically SDA, SCL. We're also going to need 3.3 volts, and we're going to need ground, which I think is this pin right here. So it's 3.3 volts, SDA, SCL, skip, and ground. So let's go ahead and make those connections on our physical board. I'm going to connect a simple TMP102 temperature sensor to my dev board. The wiring is pretty simple. VIN goes to 3.3 volts, SDA goes to SDA, which is pin 3 on the dev board, and SCL goes to SCL, which is pin 5. Ground, of course, goes to ground. I'm going to log into my board, and we're using the custom image that we created in the last episode. So login is root, default password is what we set, is Tor in this case, T-O-O-R, all lowercase. Here we can do an ls-l and we want to look at dev I2C or I2C devices, what you'll see is we've got 3 available to us in this user space area, which is I2C 0, 1, and 2. What I'm about to show you is going to demonstrate that these do not line up to the hardware bus numbers necessarily. What you'll want to do is list out all the files available in sys bus I2C devices, and you'll see the actual physical device files. And what they do is they point to a specific memory address, which we will pull up the datasheet for the MP1 and look at that memory address, and you will see that, sure enough, that is an I2C port. And that's how you can figure out where the physical I2C port maps to in Linux. You want to look at this address. This is a hex number, so 5C00200 is a specific memory address on the MP1. From what we can see here, there's only 2 I2C ports that are enabled, the one at 400.120.0.0 and the one at 5C002.0.0. It looks like 0, 1, and 2 are symbolically linked to these particular I2C files, and you'll notice that I2C 0 and 1 are the 2 different ones. I2C 2 points to the same one that's pointed to by I2C 0, and that's because this particular device, I believe, is the HDMI. So if we bring up the board data sheet, we can see that HDMI goes here, which I think provides its own I2C port, so it's a sort of a hub. And so there's 2 devices located here, so this is pointing to another I2C, I think it's a root device. I don't remember what I2C calls them. But for our purposes, what we care is that there's really only 2 I2C ports enabled, this one and this one. So if we look at the MP157 reference manual, which is not the same as the datasheet, ST keeps them separate, we want to go to section 2, and we're going to go to memory organization and the memory mapping. I believe is down here somewhere. And you could look at the peripheral bus number 5. Remember we saw the 5C00200, which is the beginning of the address of I2C port number 4. That's all the registers that are used to control this I2C bus. So this 5C00200 in Linux that we saw is really physical port 4 for our I2C. The other one we saw is on APB1, and that was 400.12.00. Here it is, 000, and that is I2C number 1. So 1 and 4 are enabled by default. We want to enable I2C number 5. So this is the address that we care about when we are going to modify our device tree and when we want to check to make sure things are working in Linux. Let's head back to our host machine. To exit, we want to Control A and then X, or I do Control A, Control X, because I'm just mashing buttons to be perfectly honest. And from here, let's head into Projects Yocto directory, and in there we want to go into the build directory. We are looking for our board name, which is STM32MP157-157D-DK1, and we're looking for a .dts file, which is a device tree source file. This might come with the board support package. Sometimes Yocto has device tree source files that are part of its default build. I think the BeagleBone Black might have a DTS file that comes with the Pokey reference distribution. Don't quote me on that, I don't quite remember. But it's something that gets copied into our working directory and used during the build process. When we find it, we don't want to modify it directly. Yocto doesn't like that, and it means that it's only temporary to our local machine. because we're creating a custom image using a custom layer, what we want to do is find a way to modify this file, either create our own .dts file in our layer, or create a patch that updates this file prior to it being used in the build process, which is what we're going to do in this episode. And I believe this is the file that we care about. So the work shared STM32 MP1 kernel sources, and this architecture or arch ARM boot DTS, and then here's our DTS file. That's the one we care about. This is the one that gets read in during the build process to create our device tree blob, which is a .dtb file. That's what gets loaded into our machine whenever we boot the kernel. Let's take a look at that .dts file to see what's in it. At the top, you'll see this dts-v1, which I suppose is the version number. And we've got a bunch of things in here that kind of look like C, but it's compiled a little differently. As you can see, there's this root node for the tree, the device tree, and it has these includes, which pull in these .dtsi, which I believe is device tree source include files. And if you scroll through here, there's really not much in this particular DTS file. A lot of it comes from these includes that are basically just copied in right where it says include to create the entire device tree. We're going to create a patch for this file, but let's take a look at a couple of the include files first, just to get a sense of what's going on with the I2C port. So I'm going to type :Q to quit since we didn't make any modifications. And the first one we want to look at is that pincontrol.dtsi file. There is about 2,000 lines on this document, so this is where a lot of the device tree source actually happens. So we want to look for I2C, so we'll hit /I2C, and you can see where some of the pins are defined. We can scroll through this, and we're looking for I2C 5, and I just passed it up. Here you can see pins A, which is one possibility where you can map I2C or I2C 5 to, it looks like port A11 and port A12, or B, where you map them to D0 and D1. Let's take a look at our board data sheet. If we go back to this pins diagram, what we want is PA11 and 12. That's the clock and SDA lines that are mapped to these pins. So PA11 and 12, PA11 and 12. So we want to make sure to use pins A and sleep pins A. I'm not super sure what sleep pins A does, but I'm fairly sure we need it, as it somehow allows the processor to put those pins to sleep to save on power. That's my guess, but we're going to need both of these, as it tells the processor to use or to map I2C 5 to port A11 and port A12 pins. Let's head out of this document, and instead we're going to go to mp15xx-dkx.dtsi. That's the one we want to look at next. Here we're going to look for I2C 5. And this is an example of how to set up a device tree node for I2C 5. If you'll notice, the I2C 5 status is disabled, which means that port is off. We're going to create a patch file that patches that .dts file, but redefines this node, and we're going to enable the status and change things like the clock frequency. We do want to make sure that we're using pins A and sleep pins A. That's what we just looked at, to make sure that I2C 5 gets mapped to PA11 and 12. Let's head out of this file. And we want to copy that original DTS file we looked at. We're going to copy that file and we're going to put it into the documents folder just as a temporary place to store it. Let's head over to documents. And we're going to copy that DTS file that we just put in here. And we're going to name it the same thing, but with a dot or orig for original at the end. So now we have two files. One is the original and one is the one that we are going to modify. So we're going to modify that first one, the one we copied in there. And we want to go to the very bottom So I just hit page down here. You can see this is the end of this device tree node, or I suppose this is probably root, which is the beginning of the device tree. Yes. So this slash means that it's the root. We're going to go down. We're going to go to the end, hit A for append, and we are going to write our own node. I2C 5. And this is information I'm basically just pulling from that DTSI file we looked at where it defined I2C 5 and making a couple of changes here. Most of this should be the same as what we saw in that DTSI file. However, we want to change the clock frequency. Now, the TMP102 that we're going to use should work at 400 kilohertz, but I'm going to slow it down to 100 kilohertz just to make sure everything works right. You're welcome to take it up to 400 kilohertz if you think things will work with your particular sensor or I2C device. And the big thing here is we want to change that status from disabled to OK. That just tells the kernel that we can use this device file and we can talk to this particular port. That's the big thing that we need to change here. Once we're done, hit escape and then :WQ to save and exit. Now here comes the hack, the trick. What is really supposed to happen is that we're supposed to have this DTS file somewhere in a Git repository, whether we cloned something or forked something from, say, the board support package, or we clone the board support package directly on our computer, make the changes, and then create a commit, whether we keep that in our own, say, GitHub repository, do a pull request, or just keep it locally. And we want to use git diff in order to create a patch after we've done a commit. But we're going to tell git, specifically git diff, to create a patch from these two files, even though they're not tracked in a Git repository. This is a pretty nasty hack, but it demonstrates how we can create a patch file and use it in our own layer to create a customized image with a specific device tree that we want to enable or disable certain peripherals. To do that, we're going to go git diff --no index, which says that these files are not part of a Git repository, and we're just going to perform a diff on two random files. The first one is going to be the original file, so we need to specify orig. And the second parameter is the new one, and we want to output that into a patch file. And if you look through Yocto Project and you see these patches, it's usually something like 0001, 0002, and they're just numerical commits that are the patch files that have been created. And we're going to create a commit message, which is usually what comes after this numerical value. I don't think this naming matters too much, but this is what you'll usually see in other parts of the Yocto project or other people's layers. So the actual name of this file does not matter, but I believe you should end it with a .patch suffix. So it's just some number, a commit message, whatever that is, and then .patch. Then we want to view the patch file, and you should see what the patch file looks like. And this is pretty common if you've ever dug into Git or GitHub, you'll see commits that look like this, and they contain these patch files. All of this should be okay, so you may want to double check things. This just says that we add our own node after everything else in the file, and this is how it notes it with the little pluses here, that things are being, or lines are being added. However, bitbake looks at these lines to figure out where the original file is and where we should apply this patch. Unfortunately, because we created it with files, these do not line up with what is expected by bitbake, and it's going to throw an error unless we hack or change these specific file names. So A is the original, B is the new one. We want to keep that. I believe these are relative. I'm not sure what A and B exactly stand for, but it's the old and the new file. And where it's going to find it is where we found the original one, which is in the working directory, but it's going to be relative to this architecture or arch folder, where we go arch arm boot DTS, and then the name of the file, which remember does not have this .orig at the end of it. So we get rid of that, and that should be the location of the original file that we're going to modify. We're going to do the same thing to the second line, and it should be named the same as the first file, because we're just going to change the file in its place. Make sure the paths and file name look the same, except for the A and the B, and we are going to save and quit. Now we want to copy this patch to our custom layer that we made in the last episode and tell our recipe, so tell some recipe that we want to include this patch and to apply it prior to building the device tree. So we're going to go to Projects, Yocto. If you have not done so already, you'll want to source pokey oe init build environment, and we're going to tell it we're going to be building things in the build MP1, which is where we've been doing stuff this entire series. Let's go up, and we're going to go into our meta custom layer that we created last episode. From here, we're going to create a recipes kernel folder, which, once again, I'm not sure if the naming of this matters, but in here, you definitely want to have Linux and STM32MP1, which is the name of your machine. And I believe this naming is important. So make sure you have that Linux STM32MP1. We're going to create those folders, and we're going to copy that patch file that we just created, which is 00 something 1. Thank goodness for tab complete. And we are going to copy this to recipes kernel, Linux STM32MP1. And just to make sure we can list the files in there, sure enough, our patch exists. Whenever you switch to the new environment that allows you to do things like bitbake, we also get this open embedded package data utility that allows us to do things like look up the kernel name. So we can run this and get the name of the kernel that we're working with, which in our case is Linux STM32MP. Notice there's no 1 at the end of that. That name is important because we want to create a bbappend file, which is a recipe that's appended to another recipe, with the name of this kernel. So during the kernel build process, our custom recipe will be appended to it. So to create this append file, and the location of it does matter, we're going to create a new file that is in recipes kernel in Linux, and we want to call it Linux-STM32MP, which is the name of the kernel that we just looked up right here. And specifically, we want to give it a version number. This version number is important because your bitbake will only apply this bbappend to a specific version of the kernel recipe that we're trying to build against, which you can look up, but for our purposes, we can do _%, which is just a wildcard that says, you know what, apply it to any kernel recipe version. We don't care. This may not be the best way to go about it if you expect kernels to be changed in the future. If you're just adding things, you're probably okay, but if you're trying to change a bunch of stuff, you may want to version control this a little better. But for our purposes, this should work just fine. So we're going to create it with .bbappend, and that suffix does matter, I'm pretty sure. The first thing we want to do is add this particular directory to the search path when bitbake is going through and looking for files to add or patch onto its whole process. In this case, this adds this own directory to the file search path. You'll notice that the _prepend says to add this particular directory to the beginning of that file search path because we want our directory to be searched first. You might be able to get away with having it searched later, but I found that this worked particularly well. The next thing we want to do is tell it what file to look for. In this case, it is the patch name. So 0001, add I2C5, user space, dts.patch, that's the file name. Notice that we do add this file : / because a source URI can be either something locally on the machine, which is what we're doing in this case, or it could be a HTTPS or FTP server. It pulls it in from wherever to copy that file to the working directory. And that's kind of the first step when bitbake is going through and trying to gather all these files together prior to patching things and then compiling things. This plus equals says to append this string, in this case the file location, to the source URI variable. And when we use this, it automatically adds in the delimiters between the various strings. In this case, it's just a space. So remember that if you're creating your own source URI, you should have spaces between the strings, or you can do plus equals and that'll automatically add spaces. So this should work for our purposes. Let's go ahead and save and exit. This should work to enable I2C5 in our custom Linux image. However, let's add a tool, in this case I2C Detect, which is a great tool for seeing if there's anything connected to an I2C port. So let's head to our build folder, if I can spell build correctly, and we can use the menu config option in bitbake specifically to configure BusyBox, which is our collection of tools that we have available to us. And you will probably need to give this a moment to run. In a previous episode, I believe I showed you how to run bitbake-c menu config for something like the kernel, so you could see how to enable and disable various kernel features. This time we're doing it for BusyBox, which is our collection of tools that we have. You can go through these and look, or you can type / in order to search, and I'm going to look for I2C Detect, which is a great Linux tool. You can see that it's in miscellaneous utilities, and it's off by default. It's not included in our build. So let's go to miscellaneous utilities and enable it. Which is down here. Luckily, these are alphabetical order, unlike the kernel options, which are not. And we scroll down again. Oh, hey, look, page up and page down do work. There's I2C Detect. We hit the space bar, and that enables I2C Detect in our build. We want to exit again, and yes to save configuration. Note that when I do this, this only applies it locally in the build folder. This has not been enabled in our custom layer, so you would have to do this every time you go to deploy the image unless we create a default configuration, which we might explore in a future episode. But for now, this is just to give us I2C Detect, which you probably wouldn't want outside of development anyway. And now we are ready for the fantastic bitbake custom image. If I can spell custom correctly. And at this point, it will likely need to rebuild the kernel because we are including a new device tree source file. So this is probably going to take longer than, say, the last episode, but not as long as building everything, which was a, 5, 6, 7 hour process. This takes about an hour on my computer, so just be patient with it, go off and do something else. Hopefully everything built for you. And now we can go ahead and flash the SD card like we've done a bunch of times before. So I'm going to plug in the SD card. Hopefully that auto mounts some things, and I will unmount those partitions. We'll go into the temp folder, deploy, images, STM32MP1, which I believe is our machine. And then we will sudo. We're going to do our dd copy if we want the st image boot file system, and we are going to copy that to our SD card, which is MMC block 2 partition 4. We're going to use a block size of 1 megabyte. We'll do the same thing, but for our custom image. And copy that to our MMC block 2 partition 5. Once again, I'm going to use a block size of about 1 megabyte. And once that's done, we need to change that extlinux.conf file for this particular board. So I'm going to unplug the SD card, plug it back in. It should auto boot, and we can use sudo vi. And I'm going to change media, my username, boot file system, mmc0, extlinux, extlinux.conf. Because we've updated the boot file system and reflashed it to our SD card, we need to make this change every time. I'm sure there's a way to script it, and I will leave that as an exercise for you to figure out how to script this part. But for now, we're just going to do it manually. So we'll update root to dev mmc block 0 partition 5, save and exit, and go ahead and unmount your partitions. You can either use the umount command line tool or be lazy like I am and use the GUI. There we go. So now I'm going to remove the SD card from my host computer and I'm going to put it into my dev board. Let's open up a new tab. I will clear everything so that we can use PicoCom to interact with our dev board. And now I'll give the dev board power so we can watch the whole boot process. With any luck, we'll be presented with a login prompt. So it is root. The password is Tor, as we changed that in the last episode. And now we want to view. Sometimes you get extra messages coming in from the kernel, which we'll just ignore. So hit enter to get a new prompt. We're going to look at sysbus I2C, just like we did at the beginning of this episode. Devices. Hopefully here we should see 40012. I believe that is I2C 1. And this is I2C 4. And then here is I2C 5, the 40015. So our kernel modification did work, which is excellent. The thing to pay attention to here are these names. So I2C port 1 is mapped to I2C-0. The one that we want to use, which is I2C5, is mapped to I2C-1, and we're going to need to remember this file name for our next episode. And then it looks like I2C4 or I2C4 port is mapped to I2C2. It's got a symbolic link in that dev folder. And then this is the hub, so we can ignore -3. And we can view those if we look in the dev folder. And these are the files, the device files that we have access to. And so what we care about is -1. Assuming we have our TMP102 temperature sensor connected correctly to the board, we should be able to call I2C Detect, which is the new tool we just installed when we configured BusyBox, -Y, and the port number, which should line up to I2C1 according to this device, which is actually I2C5 on the physical device. So if we run that, sure enough, we get our address, which is hex 48, to appear when the device is probed. And I'm going to go ahead and remove the VCC, or excuse me, the VIN connection. So the TMP102 should not be powered any longer. I'm going to run this again. And that still comes up. So let me remove all of the connections. And sure enough, it is gone. So you can see that with our device connected, we can run I2C Detect, and now we have access to that device. I'm not going to show you how to read from that device yet, because that is something for the next episode. Next time, we'll create a C program that reads data from the sensor and then prints the temperature to the console. We'll use bitbake so it's cross-compiled and built into the custom Linux image so it's there by default whenever you boot into Linux. So stay tuned for that one.